Hello, everyone. Moving right along in the old Olowski-Dean text, we're going to continue to learn about random variables, and today the goal is to start talking about random variables of the continuous type. Again, these are ones whose outcomes cannot be listed. Okay, we talked about that a little bit before. So continuous random variables are in contrast with those of the discrete variety. But before we get into that, I just want to remind you that we have this test that's due on Wednesday. Okay, so make sure you're working on that. Do not delay. Don't wait till the last minute to get going on that. Upload that into Canvas. That's like your big task for the week, no doubt about it. Okay, so just stay on top of that and be sure to reach out if you have any questions. Like I've been saying, I've been posting. If people come and ask questions either in class or in office hours, I always post those to YouTube. And generally, if I think it's something that's broadly beneficial to everyone, I will send out a communication to that effect, like an email or something. Okay, so let's get into this. Chapter 5 on continuous random variables. Okay, continuous random variables. Again, these in practice tend to come up quite a bit. I mean, any kind of data that doesn't seem to be separated out in any kind of meaningful way, but it's just all right on top of each other. Any number in an interval of values or something are possible. Things like batting averages. Technically speaking, we usually only record the first 3 digits of a batting average and we round. But technically speaking, a batting average could be anything, any real number between 0 and 1. Okay. Length of time a class starts, half-life of some kind of particle decay, right? So the graph of a probability distribution, okay, we're going to have a distribution function in this case also. Here the x-axis is going to be the random variable's possible values that it can take on. And the y-axis is going to be graphically represented by a function where the area under the curve of that function between 2 values is going to be the probability of falling between those 2 values. So we'll see that play out in practice. Again, before we had a PMF, a probability mass function, that basically assigned probability to individual points, okay? And that was our function, and it was just a bunch of points. It was a bunch of discrete points, okay? But here we have like a curve, and the area under that curve between 2 x values is going to be the probability of falling between those x values. So here we have a continuous curve for our, for our PDF, or, and before it was just a bunch of points, isolated points, okay? So this is what I just said, right? We typically will call the curve that gives us probabilities, okay? We'll work with that more in just a little bit. We call that a PDF. And sometimes we just straight up call it the density of a continuous random variable, okay? We say the density. Sometimes we call it just the distribution. But probability distribution function, probability density function, those are the technical ways of talking about this. Okay, and I already kind of mentioned this, but before, how can we add up the probabilities over an interval of possible outcomes? In the discrete case, we just added up all the individual probabilities, but here it's like between any 2 points, you have an entire interval of possible things. That's not really going to be practical anymore to add all those things together. So what do you think the analog of adding a bunch of things together is going to be? Well, integration is going to be the key. And so that's what this is. First, for finding the area under that density curve, the probability density function or distribution function, And sometimes that will involve just some basic reasoning about geometry. If you have a shape that you recognize, like a rectangle or a triangle or a semicircle or something. There's going to be tables that we'll make use of. There's tables in the text itself, out there on the web even, but also Excel is going to help us out. Sometimes we'll find known functions for the probability that capital X falls below some value little x. That's going to be the CDF, cumulative distribution function, how much probability we've accumulated so far. And of course, good old integration is also going to be key for us. So area under the curve over an interval gives a probability. So what does that mean, right? Area under the density curve gives a probability of falling into an interval. So what does that mean the probability of being equal to any particular value is going to be for a continuous random variable? Well, it has to be like if you go the integral from C to C, that's 0, okay? So being equal to any value, any particular value, the probability of that happening is 0, which is a little weird because after all, if I choose a random number between 0 and 1, I do end up getting a number. But what's weird is before we got that number, the probability of getting that number was 0, okay? So the probability of getting any particular number is 0, okay? We only talk about in the continuous case the probability of falling within an interval of possible values, okay? So that's how probabilities work. So the probability, this is very important. The probability of being equal to any value is 0 for a continuous random variable. We only talk about probability of falling into various intervals. Okay, the 3 big continuous distributions we're going to study, just like in the discrete case, what were the ones that we studied? Well, we studied the binomial, the Poisson, and the geometric, since those tend to come up in especially computer science applications the most. Okay, binomial, Poisson, geometric. We're going to talk about the uniform continuous distribution, the exponential, and we're going to spend an entire chapter on the normal distribution, which is the most important distribution of all. Okay, so we'll talk about the uniform and the exponential in this particular chapter. Okay, so let's talk about the uniform distribution. So here's an example. A bus comes exactly every 15 minutes. The wait time follows the uniform distribution. That is, you know, if I just arrive at a random point in time, then the amount of time I'm going to have to wait is uniformly distributed over those 15-minute intervals. Okay. So there are some times where a uniform distribution, so a uniform distribution, all it means is that the probability of hitting any number in the collection of possible outcomes, the probability is just evenly distributed over the entire interval. Of course, being equal to any number is 0, but the probability of falling in an interval of a particular width down here versus up here is the same. Okay, so I'm just as likely to be high as I am low as I am in the middle. That's what uniform means. Okay, so if we're sort of unsure of the distribution we're working with in a given situation, sometimes we can actually use the uniform distribution to approximate. Okay. So here's some notation. You write X and then you do the little twiddle for distributed as, U for uniform A, B, where A and B are the min and max possible values. So that is supposed to be an interval, okay? An interval from A to B. So A is the lower and B is the upper, okay? So if you wanted to choose a random number between 0 and 1, okay, and you didn't want like any part of the interval from 0 to 1 to be any more likely than any other part, then then what you have there is the uniform distribution on the interval from 0 to 1. So uniform just means evenly distributed throughout the possible values. That's what uniform means, okay? So let's look at a specific example here. So let's draw a graph of f of x. Now, what do I mean by f of x? Well, I mean the density function for this random variable. If 0 is less than or equal to x is less than or equal to 10. Okay, so f of x, before we used p of x for the probability mass function of a discrete random variable. The PDF for a continuous random variable, the notation we often use is f of x, because after all, I think that was the notation I was using back here. The graph is a curve y equal to f of x. F of x is the notation you often use. Okay, so I just want to make sure that we're clear on that. So draw a graph of f of x if 0 is equal to or less than x is equal to or less than 10. Okay, so let's go ahead and do that. Okay. All right, so here we go. So what we said was that x was distributed as uniform 0 to 10. Okay, and so we wanted to know what the PDF is going to look like in this case. Well, if we're equally likely to be anywhere between 0 and 10, then you would expect this thing to look the same everywhere between 0 and 10. Okay, so here's 0 and like here's 10, for instance. Okay, and like, so the thing is going to have the same height everywhere. So let's call that h for height. Okay, so at 0, okay, so first of all, before you get to 0, this thing is equal to 0. Here, actually, let me use a different color here, like purple. That'll be cool. Okay, let me make this nice and big. Okay, so okay, and then at 10, there's kind of an open bubble, and this thing jumps up here to this height, and it's equal to this height the entire time until I get to 10, and then it's down here, and then you're equal to that from that point on. Okay, now let me ask you a question. What should be true? Okay, what should be true about the area under this curve? Okay, so this is the graph. By the way, let me do the purple thing again. Okay, this is the graph of y equal to f of x, the PDF of this thing. So in other words, what is this? This is equal to or it's equal to h if 0 is equal to or less than x is equal to or less than 10. Okay, and it's equal to 0 otherwise. Okay. Now, what is h? What should h be? Well, one thing that should be true, since f of x is supposed to be giving us probabilities of falling into certain ranges, what if I just said that it could be anywhere? Well, doesn't that mean? Let me just say. Doesn't that mean that you know, if x could actually be anywhere in the interval from 0 to 10, what does that tell you about the area? Remember, the area under this thing should in theory give you the probability. Okay, right? So that's what that should be. So what should be true about the integral of f of x? So let me just say the integral from negative infinity to infinity of f of x dx, what should that be equal to? Well, it should be 100%, 1. Okay, on the other hand, what is this? Well, f is equal to 0 anywhere outside of the interval from 0 to 10. So this is just the integral from 0 to 10. And what's f equal to between 0 and 10? Well, that's h. Okay, and that's dx. That's that constant height h. Okay, so what is this? Well, if you think about this for a minute, this is like hx, right? H is a constant evaluated between 0 and 10. Okay, so this is 10h. Okay, so what's h? We get that h has to be a tenth. But I mean, seriously, doesn't that make sense? Look at this. Here we didn't actually have to do the integral. This is that thing I was talking about where I said sometimes you can just use geometry to determine what's happening. It makes sense that the height would be a tenth because I need the total area to be 1 and the base length is 10. Yes, the base length on this rectangle is 10. And you need, and the rectangle represents all the area, which should be 100%. Therefore, the height of that rectangle should be 1/10. Okay, so here's the graph of this thing. Okay, you see this? So here's the graph of this PDF. Okay, so here's the PDF. Here's this guy right here is the PDF of X. Okay, so that is the PDF. Sometimes we just call it straight up the density of X. Okay, okay, so there's that. And let's go back into our presentation. Okay, so we didn't just find the graph of f of x last time, but we actually found the formula for it. We saw that it was equal to a tenth anywhere between 0 and 10, and it was 0 elsewhere, right? It was equal to a tenth between 0 and 10, so that rectangle, the density looked like a rectangle in this particular case. That rectangle had area 1 over the whole interval, okay, and it was equal to 0 elsewhere. So what about the general case where I'm any kind of uniform random variable over any interval at all? Okay, so, and also, what about computing the mean? Okay, what about computing the mean of the uniform distribution? Okay, so that's something to consider as well. So first of all, another notation for that is expected value, this E of X, right? This is mu, the Greek letter mu, which means mean of this random variable X. And the mean in general, you just integrate from negative infinity to infinity. And this time you take all the possible X values and you weight it by the density, right? Weight, W-E-I-G-H-T, just like we did in the case of the discrete random variable where we took outcome times the probability of that outcome and we added them all together. That was the expected value. Same thing in the continuous case, except instead of adding everything together, we integrate X times the density, okay? And the integral kind of adds everything together, if you will, and gives you the average value, okay? And here's a formula for the standard deviation right here. I may or may not do this, it just kind of depends. But the main thing I want to do right now is to find the general PDF, right? The density of the uniform distribution, and actually find the mean as well. Find the mean. Okay, so let's go ahead and start working on that. Okay, so here's what we had in the case of the uniform on the interval from 0 to 10. Okay, but look, this picture can kind of be scaled up or down to anything at all, right? So let's go ahead and do that. Okay, so what would that look like? So what if X was distributed as uniform on any interval a to b? Well, okay, so in this case, what we're going to have, okay, so here's A. I don't know, let's just put A right here. And let's put B right there, okay? And let's use our purple pen again to try to graph the thing. So that means the density comes like this. There's kind of an open circle right here, and then it jumps up, and then it stays at that height for a while. so that this thing is evenly distributed over this whole thing. And by the way, does it really matter whether I include A or B? No, because the probability of being equal to anything is just 0. Okay, so this is the graph of y equal to, okay, hang on a second. I don't like the way that's looking. Okay. This right here is the graph of y equal to f of x. Okay, and what's that got to be equal to? Well, first of all, remember, what is this height going to be? What is this height going to be? Okay, well, the area of this rectangle that's formed by this thing needs to be 1. Okay, and the base length here, the base of this rectangle is b minus a. So the height needs to be 1 over that, 1 over b minus a, to get this thing to work out. Okay, so what is the density formula? Okay, so this is the density of x is given by, well, it's equal to 1 over b minus a if a is less than or equal to x is less than or equal to b. Okay, and it's 0 otherwise. It's 0 otherwise. Okay. And secondly, we wanted to find the expected value of x. So let's go ahead and do that, okay? So what about the expected value of x? Okay, so mu, right, also known as the expected value of x. Okay, so what is that? That's going to be the integral from minus infinity to infinity of what? X, right? You take each outcome times the density, right? The density is what weights these values properly, dx, okay? And what's this going to be equal to? Well, first of all, everything dies outside of the interval from a to b because the density is equal to 0 outside of there, okay? So it's going to be the integral from a to b of x times f of x, right? So it's going to be, 1 over b minus a times x dx. But 1 over b minus a, that's just a constant, correct? So what do I get? I'm going to get 1 over b minus a, okay? And so this thing I can essentially factor out, yes, okay? And what is the antiderivative of x? Well, that's like, 1/2 x squared, and I'm evaluating this thing between a and b. Okay, so what do I get? Well, it's going to be 1 over, let's see, I could also factor out the 1/2. So let's go 2b minus a, okay? And what happens here? It's going to be b squared minus a squared. I factored out the 1/2. But what's b squared minus a squared? That is b minus a times b plus a. Okay, so the b minus a's cancel. And what are we left with? Amazingly, we get that mu equals basically a plus b over 2. Doesn't that make sense? I mean, come on. A plus b over 2, that's right in the middle up here. Yeah, so this is that. So this is the mean, mu, which is a plus b over 2. Okay, so the mean is right in the middle, and that makes perfect sense because this random variable is evenly distributed over the whole interval from a to b. Okay, so we get the mean a plus b over 2. Okay, all right. Now, I mentioned, hey, what about, like the standard deviation and the variance for that matter? Well, okay, I said maybe we'll do it. Let's go ahead and just do that, okay? So let me just kind of explain. I spent some time in the last lecture talking about variance a little bit, and we came up with a formula for that. The formula is still true in the case, look, there we came up with a formula that we got from the sum version in discrete random variables. But it turns out that when you pass from sums to integrals, all of the same reasoning still works, because integrals behave like sums. You can still factor out constants, you can break things up, etc. Okay, so the variance of x, which remember that just measures how spread out the data is. Okay, how spread out the data is, how much is x tending to deviate away from the mean. Okay, the variance of x, the formula is the expected value of x squared minus the expected value of x squared. But we already know that mu, which is the expected value of x, we already figured out that that's a plus b over 2. Okay, so what about the expected value of x squared? Well, the expected value of x squared, all that means is you kind of do the same thing you did before, but instead of having x f of x, it's just little x squared times f of x. That's what you do in general. You always just replace like the function of the random variable with specific values in there, and then you weight it by the density. Okay, so what are we going to end up with here? Well, remember f of x was 1 over b minus a, which we could factor out. And really all that survives is the interval from a to b, and that's it. Okay? And it's going to be x squared dx. Okay, so what is this? What's the antiderivative of x squared? Well, it's 1/3 x cubed. This is going to be 1 over 3 times the quantity b minus a, x cubed evaluated between a and b, which is 1 over 3 times the quantity b minus a, b cubed minus a cubed. And you may say to yourself, oh, I sort of remember a formula for cubes. Okay, so, and what was it? Do you remember? How do you factor a cubed minus b cubed? Okay, so let's get a different color here. How does this thing factor? Well, it's going to be b minus a times b squared plus ab plus a squared. Okay, because think about that. So if I were to distribute these things through, I would end up with, let me just kind of multiply this out. So just think about it. So this would be b cubed minus, oops, sorry. B cubed, if I distribute the b, it's b cubed plus ab squared plus a squared b, and then it's going to be minus ab squared when I distribute the negative a, minus a squared b minus a cubed. So as you can see, these guys cancel. You just get b cubed minus a cubed as required. And so what happens to these things? What happens to these things? Well, this and this like cancel. The b minus a's cancel. And we are left with what? Well, it's going to be 1/3. 1/3. 1/3 what? B squared plus AB plus A squared. B squared plus AB plus A squared. Okay, the B minus A cancels. Okay, and so that works out. That works out kind of nice. So what's the variance of x? Well, it's this expected value of x squared, okay, which is 1/3 b squared plus ab plus a squared. And then we're subtracting off the square of the expectation. Yeah, that's what this says up here, the square of the expectation. So we're going to have 1/4 a plus b quantity squared. Okay, 1/4 a plus b quantity squared. Okay. So what happens here? Let's kind of sort this out, okay? Let me go over to the next, let me get a new board here. So again, variance of x, let me just rewrite this. Variance of x is equal to what? Let me see. 1/3 b squared plus ab plus a squared. Minus 1/4 a plus b quantity squared. Okay, let's find a common denominator. Let's find a common denominator. That's obviously going to be 12. So that'll be 4 times b squared plus ab plus a squared minus 3 times the square of this thing. Okay, well, look, I can go ahead and square this in place. What's a plus b quantity squared? Well, that's a squared plus 2ab plus b squared when you think about it. And all of this is over 12. Okay. Well, what happens here? How many b squareds am I going to have? Well, if I distribute the 4 here and I distribute the minus 3 here, how many b squareds am I going to have? Well, I have 4b squared minus 3b squared. So that's just going to be a single b squared. Okay, I'm going to have 4ab minus 6ab, which is minus 2ab. Okay. And then I'm going to have 4a squared minus 3a squared, which is just a squared. This is all over 12. And that factors. Isn't that just the same thing as b minus a quantity squared over 12? Okay, so there's the variance. Okay, the variance is b minus a quantity squared over 12. Okay, so there you have it. So if I wanted so this is often referred to as sigma squared, okay? Because look, remember in the formula for this thing, look at this, everything inside is being squared. So if x was in the units of dollars or something like that, then the expected value of x squared, right? The expected value of x squared, that's going to be units of dollars squared. Same thing if I square the expected value of x. Okay, so the units for the variance are squared units, which is you know, not very convenient for comparison's sake. So a lot of times, or the reason we call it sigma squared is it reminds us that the units are being squared. So sigma, that's called the standard deviation of x. It's just going to be the square root of this thing. Okay, so it's the square root of b minus a quantity squared all over 12. Okay. So remember, this was all for the uniform distribution on a to b. Okay. Okay, so we have the mean. We also had the mean equaling a plus b over 2. Okay, so look, we know lots of stuff about it. We know what the mean is. We know what the standard deviation is. So that's good stuff. Okay, so we found the mean for the uniform distribution. It's just a plus b over 2, where a is the leftmost endpoint and b is the rightmost. And we also found the standard deviation. We actually did the computation. It's the square root of b minus a squared divided by 12. All of that under the square root. Okay? So that's a pretty good bit of information that we have here. And we also found the general density. Yes, we know what the graph looks like, so that's helpful. Okay, another thing we might want to know is about the cumulative distribution function for this thing. So that's what's next, right? So for any probability distribution function, whether it's discrete or continuous, that's always just notated by capital F of x, and that's the probability that x is below, capital X is below or equal to little x. And by the way, in the case of a continuous distribution, like I parenthetically remark here, for a continuous distribution, who cares about being equal to x? It doesn't matter if I include it or don't, because the probability of being equal 2 little x is 0 in the continuous case, so that doesn't change anything. Whereas in the discrete case, you really do have to be pretty careful, okay? So just be on the lookout for that. All right, so let's go back to the previous situation where we had a uniform distribution on 0 to 10, okay? And think about what the probability of x being equal to or less than 3 is. And what's the probability that x is bigger than 3? Okay, and actually this will be fairly easy to figure out just because we have such a clear vision of what the density looks like. And then we'll try to find a general equation for the CDF for the general uniform on A to B. Okay, so let's look at both of those things here right now. All right, so here was the previous picture that we had. Okay, we wanted the probability that x is less than or equal to 3, which, by the way, is the cumulative distribution function evaluated at 3. Okay, well, 3 is somewhere right here. Okay, so that means basically what I want is this area over here. Let me just kind of highlight that in blue. Okay, that's what I want. Okay, so this is equal to the blue area, right? Because after all, probabilities are given by area under the density, yes? So what's that going to be? Well, the base length is 3 and the height is 1/10. I could integrate from 0 to 3 the function 1/10 if I wanted to, but I'm telling you, all you are going to end up getting is 3/10. Okay, so there it is. Now, what about the probability that x is greater than 3? Okay, this is where it might be a little bit surprising. It's slightly different than what was happening in the discrete case, okay? Okay, so the probability that x is greater than 3, by the way, you know, if you look at that, it's got to be 7/10, yes? It's the green area. But also, this is the same thing as 1 minus the probability. That's also the same thing as 1 minus the probability that x is, or let me just say f of 3, okay? So this is capital F of 3, okay, which is 1 minus 3/10. 1 minus 3/10, yeah? So that's another way of seeing that we can get 7/10. But this is just the green area, okay? And incidentally, that would have been the same thing if I would have said x equal to or greater than 3. That would not change that probability because this is a continuous distribution. It's a continuous distribution. Okay, and the other question that we were asked was, what is going on in the general situation here? Okay, so what is capital F of x? Capital F of x, the CDF for the general situation. What is happening? Okay, so let's kind of think about that for a minute. I'll sort of redraw this, and maybe this will be the last thing that we talk about today. Okay, so let's see. So if x again is distributed as the uniform on A to B, okay, so let's kind of draw a picture of what's happening here. So here's A, here's B. Let's draw the picture with some purple here. Okay, so the density is doing something like this. Okay. So what is happening? Well, let's think about it. So what is capital what is capital F of X? Well, what I'm going to do is, if this is the X value right here, okay, then capital F of X is going to be computing this area right here, up to and including X, right? Although being equal to X isn't really that big of a deal. Okay, so capital F of X, and by the way, this is if X is between A and B. Okay, so for A equal to or less than X equal to or less than B. What's capital F of X going to be equal to? Well, just stare at that for a minute. Okay, you know that the height here is 1 over B minus A. Okay, that's just a rectangle, so it's going to be X minus A over B minus A. Okay, it's just X minus A, that's the base length, times the height, which is 1 over B minus A. Okay, so the general CDF is just going to be, so what happens if X was below, what happens if X was below A? Well, I wouldn't have any area at all. If X was down below A, I wouldn't have any area. So that'd be 0 if X is less than A. Okay, it's this thing, X minus A over B minus A, if A is equal to or less than X is equal to or less than B. And what is the area, what is the accumulated area in the case where X is bigger than B? If X is bigger than B, remember F of X is just the probability that X is equal to or less than X, yes? If X is bigger than B, don't I have all the probability at that point? Okay, so it's just 1, okay? That is just 1 at that point, okay? So if you kind of think about this, by the way, I could rewrite this as 1 over B minus A, right? That was the height times X minus A, right? This is just, if you think about it for a minute, this is just, this is linear, okay? It is a line. It's linear with slope what? 1 over B minus A. Okay, and that's what's going on between A and B. So the graph of capital F of X, let's just kind of graph this thing. Graph of capital F of X looks something like this. Okay, so what is happening? Okay, so let's think about this. Here's A, here's B. Okay, this thing is equal to 0 before A, and it's equal to 1 after B. Okay, so let's put 1 in here somewhere. Maybe I'll put 1 right here. Okay, and let's use purple for the graph of this thing, just so we can see it. Okay, let's make this thing a little bit fatter. Okay, so this thing is 0, 0, 0, 0, 0. Okay, and then it starts taking on values of this line, okay? And this line is equal to 0 at A, and at B, if you plug in X equal to B, you get B minus A over B minus A, which is 1. Okay, and so this is the line right here, like that. And then it's equal to 1 afterwards, okay? So it's equal to 0 before, and it's equal to 1 after that. And in general, these cumulative distribution functions are going to behave this way. They're going to be non-decreasing, which means they always are moving either flat or up as we move from left to right. They're going to go to 0 as we go to the left because these are accumulated probabilities. And they're going to go to 1 as we move to the right because we're accumulating more and more and more probability as X gets big. Okay, so this is what the graph of the CDF looks like for the uniform distribution. Okay, I think that's all I'm going to talk about for now. Next time we will do an example involving the uniform distribution. And then we will look at another continuous distribution called the exponential. And after that, we'll be ready to dive into the normal distribution, the most important one of all. All right, that's all for now.